Stars are magnificent balls of burning plasma, shining brightly in the vast expanse of space. They are fueled by nuclear fusion in their cores, where hydrogen atoms fuse to form helium, releasing a tremendous amount of energy. This process releases immense energy in the form of light and heat, which radiates outward from the core. This energy needs to travel outwards through various layers of the star, and this is where the convective zone comes in. The convective zone is a chaotic region. It is like a boiling pot of water, constantly churning and moving. It plays a crucial role in transporting energy from a star's core towards its surface, ensuring that the energy reaches the outer layers. Imagine a pot of water on a stove, where the heat from the burner warms the water at the bottom. The heat from the stove warms the water at the bottom, causing it to rise to the top. This hot water rises to the top. Meanwhile, cooler water at the top sinks to the bottom, creating a continuous cycle. This cycle of rising and sinking is called convection, a fundamental process in fluid dynamics. This is similar to what happens in the convective zone of a star, where hot plasma rises and cooler plasma sinks. The convective zone is crucial for understanding a star's behavior, as it influences many of the star's properties. It influences the star's brightness, temperature, and magnetic activity, all of which are vital for the star's life cycle. It even plays a role in the formation of star spots, flares, and stellar winds, which can have significant effects on the star's surroundings. Understanding the convective zone is key to unraveling the mysteries of stars, as it provides insights into their inner workings. It helps us understand how these celestial objects live, evolve, and eventually die, shedding light on the life cycle of stars. To understand the convective zone, we must first journey into the heart of a star. Stars are like cosmic onions. They have layers, and each layer plays a specific role. The innermost layer is the core, where nuclear fusion occurs, powering the star. Surrounding the core is the radiative zone. In this zone, energy is transported primarily through radiation. Photons bounce around, slowly making their way outwards. This process can take thousands of years. Think of it like a crowded room where you're trying to move through by squeezing past people. Finally, we reach the convective zone. This zone is located above the radiative zone. In some stars, like our Sun, the convective zone is in the outer layer. In other stars, it might be closer to the core. The location and size of the convective zone depend on the star's mass and age. Now, let's dive into the heart of the convective zone, a region where the dynamics of energy transport are truly fascinating. Here, energy transport takes a different turn, shifting from radiation to a more dynamic process. Instead of radiation, convection takes center stage, playing a crucial role in the star's energy dynamics. As hot plasma rises from the bottom of the convective zone, it carries energy with it, moving towards the star's surface. This energy is released into space as radiation once the plasma reaches the surface, illuminating the cosmos. Think of it like a lava lamp, where the heated wax rises, cools down, and then sinks back down. The heated wax rises, cools down, and then sinks back down, creating a mesmerizing cycle. This continuous cycle of rising and sinking creates a turbulent environment within the star. This is what we call convection, a fundamental process in stellar physics. This process is vital for transporting energy from the star's interior to its outer layers, ensuring the star's stability and luminosity. The efficiency of convection depends on the temperature difference between the bottom and top of the convective zone, driving the movement of plasma. The larger the temperature difference, the more vigorous the convection, leading to more dynamic energy transport. This difference in temperature is what drives the constant churning and mixing of the plasma within this zone, maintaining the star's energy balance. The convective zone is not just about energy transport, it has far-reaching consequences for a star's behavior. One of the most striking examples is the formation of sunspots and solar flares. Sunspots are cooler, darker regions on the sun's surface. They are caused by the sun's magnetic field. The sun's magnetic field is generated by the movement of plasma in the convective zone. This magnetic field can get tangled and twisted. When these tangled magnetic field lines snap, they release a tremendous amount of energy. This energy is what we observe as solar flares. Another important phenomenon driven by the convective zone is stellar wind. This is a stream of charged particles constantly flowing from a star's surface. The convective zone plays a crucial role in accelerating these particles and propelling them into space. Section 5, Convection's Variety, a tale of different stars. The convective zone is not a one-size-fits-all phenomenon. It varies significantly across different types of stars, influencing their behavior and evolution. Its size, location, and behavior vary greatly depending on the type of star. This diversity in convective zones is a key factor in understanding stellar dynamics. In small, cool stars like red dwarfs, the convective zone extends all the way to the core. These stars are fully convective, meaning their entire interior is in constant motion. These stars are fully convective. This means that their entire interior is like a giant boiling pot, with material constantly moving and mixing. This constant churning helps to transport energy from the core to the surface, making red dwarfs incredibly stable and long-lived. In contrast, massive stars have a small convective core surrounded by a radiative zone. These stars are like onions with a tiny churning center. The convective core in massive stars is responsible for mixing elements and transporting energy, but it is much smaller compared to the radiative zone that surrounds it. The convective zone in massive stars is responsible for dredging up heavy elements from the core. This process enriches the outer layers with new elements. This process has significant implications for the star's evolution and its eventual fate. It influences how the star will age and what kind of end it will meet. Our Sun, a middle-aged star, has a convective zone in its outer layers. This zone plays a crucial role in the Sun's overall behavior and activity. This zone is responsible for the Sun's magnetic activity, including sunspots, solar flares, and the solar wind. These phenomena have a direct impact on space weather and life on Earth. Each type of star with its unique convective zone showcases the diversity and complexity of stellar interiors. Understanding these differences helps us comprehend the vast and varied nature of the universe. Section 6, the magnetic maestro convection and stellar magnetism. The convective zone is not just a boiling cauldron of plasma, it's also a giant dynamo. It generates a star's magnetic field. This magnetic field is crucial for a star's life. It influences the star's rotation, its interaction with its surroundings, and its evolution. The magnetic field is generated by the movement of charged particles within the convective zone. This movement creates electric currents. These currents in turn generate magnetic fields. Think of it like a bicycle dynamo. The rotating wheel generates electricity. The strength and complexity of a star's magnetic field depend on the properties of its convective zone. Stars with larger and more turbulent convective zones tend to have stronger and more dynamic magnetic fields. These magnetic fields are responsible for phenomena like sunspots, solar flares, and coronal mass ejections. Section 7, Stellar Evolution, Convection's Role in a Star's Life. The convective zone is not static, it evolves with the star. As a star ages, its internal structure changes. This affects the size and location of its convective zone. These changes have profound consequences for the star's life. They influence its brightness, temperature, and lifespan. In some stars, the convective zone can expand or contract. This can trigger changes in the star's activity. For example, as our Sun ages, its convective zone is expected to shrink. This will lead to fewer sunspots and a weaker solar wind. In other stars, changes in the convective zone can lead to more dramatic events. For example, in some giant stars, the convective zone can dredge up fresh fuel from the star's interior. This can cause the star to brighten and expand. Section 8. Unlocking Stellar Secrets. Studying the convective zone. Studying the convective zone is challenging. We cannot directly observe this turbulent region. It is hidden beneath a star's surface. However, astronomers have developed ingenious techniques to probe this hidden world. One technique is called helioseismology. This involves studying the vibrations on a star's surface. These vibrations are caused by sound waves traveling through the star's interior. By analyzing these vibrations, astronomers can map the internal structure of a star. This includes the convective zone. Another technique is to study star spots. By tracking the movement of star spots, astronomers can learn about the rotation of a star's convective zone. This provides valuable insights into the dynamo processes that generate a star's magnetic field. Section 9, a symphony of energy, convection's enduring legacy. The convective zone is a symphony of energy. It is a chaotic dance of heat and matter. It is a powerful engine that drives a star's activity. From the smallest red dwarfs to the most massive supergiants, the convective zone plays a critical role in shaping the lives of stars. Understanding the convective zone is crucial for unraveling the mysteries of the cosmos. It helps us understand how stars are born, how they live, and how they eventually die. It also provides insights into the formation of planets, the evolution of galaxies, and the ultimate fate of the universe. As we continue to explore the cosmos, the convective zone will undoubtedly continue to captivate our imagination. It reminds us that even in the depths of space, there is beauty and wonder to be found in the most turbulent of places.